right, let's take a look again at a little bit more diving into a unit vector. And there's another way that we can describe it so that we can force an expression to be a unit vector. So that's what we're going to talk about here. So recall that a vector u, for which u in the double bars is equal to a value of 1, is called a unit vector. Okay, so they have an example here, just like a unit price at the grocery store can be found by taking the price of an item and dividing it by the number of units it contains. So if it has like 10 servings, you can take the total price of that box and divide it by the number of servings, and it will tell you how much one serving is. A unit vector can do the same type of thing. So each of these that we're going to talk about is, say, a box of cereal, and we're going to divide it into its portion size so that we can figure out what the unit vector component is. Okay, so unit vector in the direction of the V theorem, for any non-zero vector V, the vector u is going to be equal to the vector v divided by the magnitude of v. So that unit vector does have direction, mind you. So the fact that you're taking that unit vector and then dividing it by just the magnitude gives you that 1, but it also says whether it's supposed to be positive or negative depending on the direction that it's going. Okay. A variation of this, you guys know that I use those magic triangles, right? So if we know that u is equal to v over the magnitude of v, then we can also say that v is equal to my unit vector times that magnitude. Okay, so if I know what my unit vector is, I can get my actual vector by multiplying that unit vector times the magnitude of what I've got. All right, so let's go ahead and take a look at an example. This is a little bit kind of, until you see it done, it can be a little confusing. So we want to find a unit vector that has the same direction as v equals 12i minus 5j. And how can you confirm that your answer is correct? Okay, so we know that to find our unit vector, we've got to take the actual thing itself, which is this, right? And we've got to divide it by the magnitude. Well, how do we find the magnitude, right? We take the square root. So I'm going to go ahead and find what v is. I know what this v is, right? So now I got to find v. So this will be the square root of 12 squared plus negative 5 squared. So that's going to be the square root of 144 plus 25, which is the square root of 169. And that is actually a value of 13. So my vector has a magnitude of 13. So now it wants me to take my v value, which is 12i minus 5j, and I want to divide that by my magnitude. So divide it by the magnitude, and I've got it. Okay, so how do you check it and confirm that your answer is correct? Well, this right here is actually u. That's my unit vector. And remember, I said I could take that unit vector and multiply it by my magnitude, and I would get my original vector back. So all I have to do is multiply this thing by 13. I lose my denominators, and I'm back at my 12i minus 5j. So to find the unit vector, you take the current vector you have, and then you find what the magnitude is of that vector and divide that into it. Okay, so let's find a vector from its direction and magnitude. So here we've got a ball that's thrown with an initial speed of 90 miles per hour. So this is miles per hour. That is going to actually be the magnitude. Okay, that's a number. The magnitude is 90 miles per hour. When the ball is released, the angle it makes with the horizontal is 30 degrees. So that value is actually going to be the direction. So I can get my direction in degrees. So it's going to have that drawing below. All right, so here's what I want to do to find the terminal point of the vector, which is this point right here. Use what you know about trigonometry to find the x-coordinate. Well, remember my x-coordinate r cosine theta. Remember that? So my r is 90, and I'm going to do the cosine of 30 degrees. So that's how I'm going to get it. And then the y-coordinate is going to be r sine theta, and that'll be 90 times the sine of 30 degrees. So let's go ahead and write this. So we've got 90 times the cosine of 30, I, so that's my x direction, and then sine of 30 degrees, j. And when I distribute that 90 through there and actually do the math on it, right? So if I do 90 cosine of 30 degrees, I get a value of 45 times the square root of 3. And then, so that's my x. And then my y is 90. And this is the same as my I. And this is the same as my j. Not cosine, we need sine. So 90 sine of 30 degrees is 45 because the sine of 30 degrees is just 1/2. So I could say that it is 45 root 3I plus 45j. Of the initial speed, how much is in the horizontal direction? Well, let's go ahead and take a look. We said that it was 45 root 3. And if I do the math on that and actually put the square root of 3 in there, I get a value of 77.94 miles per hour. Okay, so what I did was 45 times the square root of 3, which is like 1.73. It's just shy of 2. Of the initial speed, how much is in the vertical direction? Well, we already figured that out, right? That is 45 miles per hour on that one. Okay, so pretty easy application. We've seen this type of thing before where we have our polar value, so both my r and my theta, this is the same type of thing, right?